Hello, bright minds. Have you ever wondered what really happens when you switch on a fan or a bulb? It's all thanks to something called electric current, the electrical traffic sipping through wires to power your favorite gadgets. Here's a quick joke to spark us off. Why did the electron break up with the proton? Because it found the relationship too negative. Now, electric current, symbolized by capital I, is basically the rate at which electric charge flows through a cross-section of a conductor over time. Imagine a busy highway where the cars are charges. Current measures how many cars pass a checkpoint every second. Mathematically, electric current I equals the charge Q divided by time t, where Q is in coulombs and t in seconds. So when we say 1 ampere, or 1 amp for short, it means 1 coulomb of charge flows through in 1 second. A steady current means this flow isn't changing over time like a calm, steady river of charges. Understanding this helps us grasp how electronic devices get their juice. Let's take that electric current and see how it travels through something called an electric circuit. Think of it like a merry-go-round, a continuous and closed path where electrons love to keep moving. An electric circuit typically includes sources like cells or batteries, conductors such as wires, and loads like bulbs or resistors. For current to flow continuously, the path must be closed. If there's any break, the flow stops, just like you can't run a race if the track is incomplete. The battery acts like a pump, maintaining a difference in electric potential to push charges around this loop. Along the way, we often control or measure the flow using switches to start or stop current, resistors to limit it, or ammeters to measure how much current is flowing. These parts make sure our circuits work safely and effectively every day. Here's a little twist in our electric story: the direction of current. Electrons actually move from the negative terminal to the positive terminal, kinda like swimming upstream towards higher potential. But wait, when we draw circuit diagrams and talk about current direction, we use the opposite. Conventionally, current is shown flowing from positive to negative terminal. This old tradition dates back to before scientists discovered electrons, so it stuck around like an old nickname. So while the real charge carriers, electrons, move one way, circuit laws and symbols use the conventional direction to keep things consistent. It's like how we drive on the left or right side of the road, just a rule everyone follows. Remember, this direction tells us the net movement of positive charge, which is why it's still very useful in understanding circuits. Let's get hands-on and connect charge and current with some numbers. If Q coulombs of charge pass through a fixed point in t seconds, current I equals Q divided by t. In words, current equals charge over time. For example, if 10 coulombs of charge flow in 5 seconds, then the current is 10 divided by 5, which is 2 amperes. Easy, right? But here's a neat fact: charge isn't just continuous, it comes in discrete chunks. This means charge Q is actually equal to n times E, where n is the number of charges and E is the elementary charge, approximately 1.6 times 10 to the minus 19th coulombs. So every time charges move, they move in tiny packets, sort of like grains of sand. This quantization is why electricity behaves in very predictable ways when you dig deep enough. Let's picture a simple electric circuit. Imagine a battery, some wires, a switch, and a resistor that acts like a load, say a bulb. When the switch is open, the path is incomplete and no current flows. It's like a broken bridge. But as soon as you close the switch, the circuit closes into a loop and electrons start drifting through, propelled by the electric field inside the conductor. The cool part? In a series circuit like this, the current is the same everywhere. What the battery sends, the resistor and the wires all carry equally. If you place an ammeter in series, it directly measures this current across the resistor branch. Visualize it as checking how many cars pass a toll booth in one lane, same number everywhere on that lane. This uniformity keeps our circuit calculations neat and predictable. Let's solve a quick example to get comfortable with these ideas. Suppose a total charge of 480 coulombs passes through a wire in 4 minutes. To find the current, first convert 4 minutes into seconds, that's 4 times 60 or 240 seconds. Using the formula current I equals charge Q over time T, we substitute the values 480 coulombs divided by 240 seconds equals to amperes. That means a steady 2 ampere current is flowing. This is a reasonable current value for everyday appliances like a 100-watt bulb working on a 220-volt supply. So not only do we perform calculations, but we also relate them to familiar things around us. To wrap up, electric current is simply charge flowing over time, or I equals Q divided by T in words. Remember, the charge itself comes in multiples of a tiny elementary charge E, about 1.6 times 10 to the minus 19th coulombs. In circuit diagrams and real-world electrics, conventional current direction flows from the positive to the negative terminal, even though electrons actually flow the other way. And crucially, for current to flow continuously, the electric circuit must form a closed loop, no breaks allowed, just like a perfect racetrack. Keep these ideas in mind, they form the foundation for understanding how electricity powers our world. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.